right, well, thank you everyone for coming today, the last week of the official teaching period of this semester, with snow squalls and all. So I'm Michelle Sarrazin. I'm an assistant professor in chemical and biological engineering and an affiliate faculty here with the Andilnger Center. It's my pleasure to introduce our Andilnger Center highlight speaker, Professor Paul Dauenhauer from University of Minnesota, who is currently a distinguished McKnight University Professor there in the Department of Chemical Engineering and Material Science. He is also the Zolt Rumi Innovation Chair and MacArthur Fellow as well, and is the director of the Center for Programmable Catalysis, Programmable Energy Catalysis, which is some of the work that he'll be talking about today. Paul's a pioneer in the field of catalysis and reaction engineering, which is my area, my home. And so it's been so nice to see all of the amazing work that comes out of Paul's groups over the years and having him in our community. He's won too many awards to really go through. I mentioned the MacArthur Genius Award, as well as early careers such as NSF DOE Camille Dreyfus Award, and the AICHE Young Investigator Award as well. Outside of the lab and in the academic setting, he's also been a founder of a few different companies. Carba, Lacreel more recently, Activated Research Company, for those of you who use methanizers and other components in your GCs. It's a very good brand, and I got to see a couple prototypes because one of his colleagues was a PhD student in the same lab as me, so we got to play around with some of the early polyarcs on the GCs there. And so I don't want to take any more time because he has a lot of cool science to talk about, so Paul, the floor is yours.
Thank you. So thank you for the introduction. I want to talk to you about this idea of programmable catalysis. And this is an idea that I've been thinking about for about 10 years, and we only really started on it 5 years ago. And it's just taken off and grown with a large number of us working together. So let me dive right into this. If we think about catalysis, heterogeneous catalysis in particular, we're usually thinking about structure-function relationships. We have some chemistry in mind. We usually have some conditions dictated by thermodynamics or processing conditions. And we think about the surface or active site structure or encompassing environment that can control that chemistry to make it fall down a free energy gradient. And this has given this focus on new materials, new active sites, and the idea that we can relate the structure of whatever we make to the performance. And of course, this has been wildly successful for a lot of chemistries. And we look at the array of different materials that have been made in the past 20 years, especially with new advances in nanotechnology synthesis and characterization. And this, of course, is very exciting, very successful. I'm not saying anything negative about this. For a lot of things we're interested in energy, the way I'd phrase it is this isn't sufficient for what we want to achieve. And I'll give you the example here. With the wind and solar technologies are now extremely low cost, and we have the ability to implement them on a gigawatt scale. But a lot of times we don't because we have to integrate them into the existing infrastructure. Now, if you could install wind and solar anywhere you wanted on the planet and utilize that energy in some fashion, we could accelerate dramatically the use of renewable energy. And one way that people are talking about doing this is storing it as chemical energy. So taking water, CO2, and air, reacting it in some way to make hydrogen, ammonia, and methanol. Now, these are, of course, classic catalytic reactions, and they all have the same thing in common, which is they're fundamentally limited by the approach of catalysis that we've been pursuing. So if you're familiar with these, a long time ago, there was a French chemist named Sabatier who said that he generally said in words, there's an optimal binding energy of molecules on surfaces. If they bind too strong, they don't react. If they bind too weak, they don't react. In the 1960s, a group of scientists put together these ideas quantitatively and said that they formed at these peaks that we now know as the Sabatier volcano. It's a very simple idea, if you haven't heard of this before. On the independent axis of any of these plots is a descriptor of that material. So in this case, it's the binding energy of a molecule on that particular material. So molybdenum, iron, ruthenium, osmium, cobalt, and nickel. And the vertical axis is the reaction rate. And what you see is for all three of these chemistries, there's known materials at the peak of those Sabatier volcanoes, which are the fastest materials we know. The Nobel Prize was awarded over 100 years ago for discovering that iron, ruthenium, and osmium are very fast reactions for ammonia synthesis. On methanol, copper is our best material. And for producing hydrogen, the oxygen evolution reaction, iridium oxide sits right up here at the top. It's a good performer. It's not as good as we would like, but it's extremely rare. So all three of these have this fundamental problem with how we do chemistry. Now, if you think about what we do, our conventional strategy is we pick that chemistry, we pick the conditions such that the reaction will proceed thermodynamically downhill. So whatever chemistry we have, we pick the conditions, we let the molecules fall down this free energy gradient, and then we pick a material that tunes that free energy gradient so they fall down it as easily as possible. And that, of course, has been successful for us. But I want to propose as an alternative. We don't have to necessarily pick the overall conditions if we can take a free energy surface that changes with time and promotes kinetically molecules in one direction, forwards or backwards. At this point, we essentially have a catalytic pump. The energy of the reactants and products aren't changing, but the free energy of the surface-bound species are changing, and with that, the transition state energy such that molecules are able to accelerate from the reactant to the product. Now, this idea is, I would say it's been around for millions of years because biology found this a long time ago, and it exists. It's what keeps our bodies functioning. It keeps the molecules and ions in our body going to equilibrium where we would die. But the idea here, what happens is because molecules that are binding to surfaces change differently with perturbations like this, you end up with this formation of a mechanism called a ratchet. And this is the ion pump mechanism that exists out there. And there's two different variations of ratchets here I'm showing you. This one on the left is called positive scaling, where all the molecules move together. And the one on the right is called negative scaling, where one molecule weakens in binding energy and the other one strengthens. But either way, you can see that there are different conditions for different things to happen in the mechanism. A reaction is a series of things that happen: adsorption, reaction, desorption, and usually in real chemistry, many more things. So these exist out there, and that became very important to me because when we started to see all of these interesting catalytic phenomena, I got a little worried about how this was proceeding. There's a really great book that takes these ideas from fundamental principles, first and second law of thermodynamics, all the way up to how biology proceeds, and we can use these same ideas over here. Another way I like to present this to people, and I like to present it because it helps us think about more complex chemistry, is these very simple ideas. Static catalysis is very much like downhill skiing. We have high energy reactants, and we create these free energy surfaces where hopefully molecules can fall down that surface as quickly as possible. And if we're trying to do selective catalysis, we want them to fall one way versus another. If we're trying to make one product, hopefully all the molecules are nudged down that free energy gradient to the right rather than to the left, or vice versa. But what we're talking about here is more like surfing. The surface of the ocean overall is generally flat, but local free energy gradients, the waves, can promote molecules forward. Now, this is fundamentally different from what's been pursued quite a bit for the last half century of what else can we vary in a catalytic reactor or process system. We can, of course, change the temperature, where we're changing the overall thermodynamics of the reaction over on the left. In the middle here, you can change the overpotential, which you're changing, again, the overall thermodynamics. If you give enough overpotential, you can drive a reaction downhill fast enough. And over on the right, if we just are changing the catalyst itself, we're only changing the molecules on the inside. And that gives you fundamentally different behavior and efficiency than the systems on the left. Another way that I think helps people think about this conceptually is looking at it in terms of what's changing in terms of time scale, but also whether it's forced or passive. So we have, of course, in catalysis, all the things that can change on surfaces with time. So we have activation, deactivation, we have reactor instabilities, we have process instabilities. All of those things, of course, exist. But on the forced side, things that we could actually change with time, we could do things like chemical looping at the process scale. For reactors, we can change overpotential, temperature, pressure, compositions, all those kind of things. But over here is where we want to focus. Variable binding energy, surface entropy, cavity or sterics. I want to change the actual active site with time. So when that's the case, what I want to think about is rather than going from material A to material B to material C, I want to think one material, and I want to change its properties on command. So I want to take this one specific metal, for example, and I want to have the ability to switch it between state 1, state 2, and state 3. And when I do that, for this simple depiction here of carbon monoxide binds stronger from state 1 to state 2 to state 3, and if that dissociates to carbon and oxygen, carbon and oxygen also exhibit different binding energy variation with my modulation of this material. So carbon and oxygen bind weakly here, they bind stronger here. And with our linear scaling relationships, we can predict the relationship between the reactants and products. That's our slope and offset here, gamma and delta. And the transition state energy also changes with a BEP relationship. So I can predict whether this barrier is high, if it's going uphill, it's medium, or low. Which means I could put my catalyst in state 3 here where there's a low activation energy. Now, how would you do something like this is something we've been thinking about a lot, and we've broken it down into 4 different categories. So one of these, of course, is you can change something like a protein or a surface using an input like a reaction. So you could flip conformations of material. That's a stochastic approach, so you have some control over that. The 3 programmable approaches where I have complete control over what's happening fall into 3 categories of dynamic strain, dynamic pulsed illumination, or dynamic charge condensation. So our center focuses on number 2 and number 3. Phil Christopher at the University of California, Santa Barbara leads this effort, and I lead this effort over here with Omar Abdelrahman at the University of Houston. So I'll talk about this right here for a little bit, and I'll show you how it works. And then I want to talk about the implications of it, and that's how I'll end the talk with some real chemistry. So the idea is very simple. If chemistry is about electronic interaction, if I change the electron density of an active site, I'm changing its chemistry, I'm changing its binding energy. So the very simple idea is let's just accumulate electrons or holes in the active site on command. And we can do that with this setup right here, which is a capacitor. I can take a conductive surface. On top of that, I can put a high K dielectric material. I put a sheet of graphene on top of that. And then I can put on top of that any active site I want. In this case, I'm going to use alumina, which is not a conductor, but when it's this thin, I can get electron manipulation over that thin area to the active sites. And on top of that, then, I have a defect site on alumina where I can do dehydration catalysis. It's an acid catalyst. And I'm not inherently interested in isopropanol dehydration, but it's a good probe reaction. We know a lot about it. So isopropanol dehydrates to form propene. So the idea being, if I apply a potential now, I could remove electrons from that top layer and presumably make alumina more acidic, and vice versa. So here's the device. That's an actual picture of it right there. That's a gold contact I use to touch the top of the device. This is a 3D depiction of it. And over here, my colleague, Andre McQuain, has sliced this with a focused ion beam. You can see here, this is the hafnia. There's a sheet of graphene there, which you can also see that right there. My alumina is right on top, and for the imaging, we've added the carbon, but that's not normally there. So here's the idea. I'm gonna take this device at low temperature. I'm gonna put isopropanol on top of it, and then I'm gonna ramp the temperature with time, and eventually I get, for any catalyst, sufficient energy for that to react, and I'll see propene be formed. So for conventional materials, tungsten oxide, alumina, titanium, zirconia, this is well known. The temperature at which I see propene formation for tungsten oxide and alumina is much lower in temperature. It's a better catalyst than titania, and zirconia is a much worse material. So these are our discrete options. We can pick a material, and that will give one performance for that particular active site. Now for this condenser approach, where I'm going to be condensing electron density at the active site, I could start with a material like alumina, so I could put that on the top. And then as I remove electrons from it, I'm going to slide this to the left. And this gives me this continuum opportunity to control the surface chemistry. So the first thing I care about is how many electrons do I remove from that surface in general. And it turns out that's really easy to do because I just measure the current and integrate with time. So here's a measurement we do all the time. We make a device, we apply a voltage, we integrate the current, and we measure how many electrons we remove. So we're interested in how many electrons we remove per square centimeter, and for different voltages. And so what you can see is if I just make a device with graphene, but there's no alumina on top, I have a certain number of electrons I remove. And then when I add the alumina on top of that, I remove even more electrons from that surface. Now the question is not just how many electrons I remove, but how many I remove relative to how many active sites there are. So over here on the right now, you can see that for the device I'm going to use, the alumina active site material, this dehydration catalyst, I remove about 10 to the 13 electrons. And there's about 10 to the 14 active sites per square centimeter. So on average, if electrons just evenly distributed, which they don't, I would remove about 10% of an electron from an active site, which is a lot. Okay, so now when I do this, I can see, well, what is the effect on the chemistry? I can do the experiment I was talking about earlier. So what you're seeing here are 4 different applied voltages. So I've changed the catalyst with this applied voltage. And you can actually see the propene formation in a vacuum system with a mass spectrometer. So here's my normal propene peak right here. Here's the propene peak with 1 volt, 2 volts, 3 volts, and it's sliding to the left. It moves gradually here. If you do this enough times, you can get good statistics, but you can definitely see that +3 and 0 are quite different. And from that now I can back out what is the activation energy difference between my different materials. So I'm changing the binding energy of isopropanol, I'm changing the activation energy, and when I remove those electrons with +3 volts, my activation energy dropped by about 20 kilojoules per mole. So that tells me I have the ability to kind of turn this dial to change the acidity of the material itself. Now, what direction should it have gone? We can compare with computation. So my colleague Matt at the University of Minnesota has taken this known defect site on alumina, put isopropanol on it, and calculated the binding energy change of isopropanol and the transition state energy, and it matches up pretty closely. He did a little more. He removed about 12.5 electrons per site, and he got a little bit higher change in the activation energy. So they're about comparable. So what we're really doing, we're trying to take materials and change them on command using an applied potential for a non-Faradaic reaction. So this is thermochemistry that's electronically modulated. So we're taking this alumina and making it behave like a superalumina. So my students and I we joke that we call this electronic alchemy. We wouldn't put that in a paper, of course, but that's what we like to think of it as. So this is, of course, a platform device. There's nothing special about alumina. In fact, it's kind of a weird option because for us to remove the energy density from that active site, it's a gap state. What I'd really like to do, though, is modulate metals because we use metals for so many important reactions for energy applications. So I think of this as a platform device. I have my graphene layer here to move charge across the surface, but I can put anything on that, presumably, that I want. I care about the overall capacitance because I want to know how many electrons I add or remove, and I care about the speed, how fast I can get electrons across that surface and back, for the reason I'm going to show you in a bit. But on top of this now, I could put many different materials. I can make them of different compositions, all these kind of things. So let's just put metal clusters on. So now we put about these 2 nanometer to 3 nanometer thick clusters of platinum. There's many layers here, so you can actually see some sit behind, some sit in front. They're a couple nanometers thick, but they're more like pancakes when we deposit these. And the idea now is I'm going to do the same experiment, but I'm going to put carbon monoxide down. Of course, this will bind all in different places. And I'm going to measure the binding energy of that molecule when I add or remove electrons from it. So when I do this now, look at the data on the left. So the data on the left, they show the desorption of carbon monoxide. So carbon monoxide binds to platinum, and it comes off at about this temperature right here, which I can read off about there. Now, as I add electrons to that, I apply a negative bias. I'm weakening the binding energy of CO, and it comes off at a lower temperature. And as I remove electrons from CO, it slides to the right. It gets wider because I'm changing the way the electrons distribute in the platinum. Now, that's for platinum nanoclusters. If I put a thicker layer of platinum on that, I get a screening effect. So the carbon monoxide on the top doesn't feel the electronic effect, and all of the peaks look the same no matter what bias I apply. So the effect has to do with the charge modulation of those particles on that surface. And again, I'm taking platinum and giving it properties that are electronically different than conventional platinum. And you can see that here on the bottom right where I summarize this. This is the peak temperature position as a function of the applied potential. So I've changed the binding energy of carbon monoxide about 20 kilojoules per mole, about 0.2 eV. So I'd like to do this more. I'd like to have a much larger effect. I'd like to increase this by at least a factor of 3, if possible, 5 preferable. And so I want to look at different materials that give me more electron density. And one of these is, a lot of these are known in the semiconductor and device world, is what's called an ion gel, where I take a polymer and an ionic liquid, I mix this together, and so instead of a solid oxide, I have a flexible material here. So we coat an ion gel, we put carbon on top of that, and then we deposit our active site platinum on top of there. And you can see now I have this flexible device that I can spool into high surface area devices. This is a very powerful device, I'll show you that in a minute, but the drawback of it is it's only stable up to about 200 degrees C. So for a lot of catalysis applications, it won't work, but it will work for some. So here the benefit is if I go back and ask that experiment, how many electrons do I remove? I can again just apply a voltage, integrate the current, and measure it In purple here, this is the total number of electrons I was removing before. I've increased this by about a factor of 10. And at temperature increases, this goes up as well. So if I come over here to the right, I'm now, before I was removing about 10 to the 13 electrons per square centimeter, I've increased this up to about 10 to the 14 electrons per square centimeter. And the density of active sites is around the 10 to the 15. So in the best case scenario, this is about the maximum we think we could ever get for total electron modulation. But we should be able to see this effect increase significantly. Now, another way we can evaluate this effect is not with temperature-programmed desorption in a vacuum chamber, but is with infrared spectroscopy. So we're going to take this device now. It's a more powerful device than the one I was showing you a minute ago. We'll put it in this chamber here. We'll do a single bounce of infrared light, and we'll look for the carbon monoxide on platinum peak, and then we can track that as we change the conditions. So this is now a thermodynamic measurement. I'm measuring an equilibrated gas and surface adsorbed carbon monoxide. So that's what you're seeing over here. The maximum signal I get, a clean surface, and then everything in between as a function of the temperature and the applied voltage. So normally at 0 volts, you would get an isobar right over here that I can fit. And then if I apply a positive bias, I'm strengthening the binding of CO, so it comes off at a higher temperature. And as I apply stronger and stronger negative biases, I'm adding electrons to the platinum, I'm weakening the CO binding energy, and I'm shifting to the left. So if I sit right here at 125, I should be able to basically turn that surface on or off. I can have a surface covered in CO or a surface that's basically vacant. So this is good. This is a really powerful device, but again, it's not temperature sensitive. So our center has multiple materials people working with me to try to make devices that are temperature stable, robust, and high electron density. And so one of the devices we've also been looking at in parallel is what's called a nanolaminate. So it's the same device, except instead of an ion gel or hafnia, we're putting right in here this nanolaminate of alumina and titania layers. So instead of just growing hafnia, we put a thin layer of alumina down, then a thin layer of titania, then a thin layer of alumina. This idea has been around in the semiconductor world for a while, but we're applying it here for this large surface area application. Large surface area being 1 square centimeter. So when we take this device here, you can see it's just the same structure of everything we used before, but we get more electron density than with just a hafnia device. So let me kind of put all this together in this plot on the right. This is the modulated binding energy of carbon monoxide. This is the electron density that's been removed for platinum atom. And I can put the 3 devices I was just showing you on this simple theory line. So hafnia is a good material because it's easy to work with. The ATO is higher temperature stability, and 5 times more powerful. The ion gel is more powerful, but it's not temperature sensitive. So we're still pushing the limit of what we think we can make for devices. The flip side of this is we also care about speed. I haven't told you why we care about speed yet, but in these devices, we can measure the capacitance as a function of the frequency of charge we apply, and we don't have a significant drop-off until about 1,000 hertz. So we can make these things even faster. There's other tools out there to do that, but 1,000 hertz is going to be fast enough for what we're trying to do right now. Okay, so building up all these ideas, we now have the ability to take a surface. This is an alumina surface here. Obviously, this is a cartoon. But the idea is if I can send a signal to a device, to a catalyst surface, and tell it the properties I want at an instant in time, then I have to think of this in terms of design. What signal do I want to send a surface at any moment in time to make the chemistry do what I want? And that's the idea of programmable catalysis. A program would essentially give an input signal that would be optimized for that particular chemistry. Now this is actually where we started 5 years ago. And if I go back to the energy problem we started with, we can go back to this idea of the Sabatier limit. The vertical axis here is the reaction rate. The horizontal axis here is the binding energy of molecules. That's our descriptor. And here you can see this Sabatier volcano. So if this was ammonia synthesis, ruthenium and osmium, and iron would be up near the top here. And that's the fastest we could ever go. So the way to think of this really is not that these materials are that great. They're average at everything. If I think of this side over here, by linear scaling, that's the rate of reaction on the surface. That keeps going. If I was to find a material that could desorb quickly, I would get rates that are up here. And over here, this is the desorption rate. If I could go to the left of the material, I can desorb molecules very quickly. And so the material that sits in the middle here is kind of average at everything. But if I could make a material that changes with time, I could slide left to right. And if I could slide left to right fast enough, I could exist here for a moment in time and there for a moment of time. And so the question is, how far can I slide left to right? That's the device power. And how fast can I do that? And what speeds do I need to get up here? You can actually read that off of here, about how fast you need to go. Okay, so when I'm changing a material with time, I'm changing everything. All of the surface energies are changing. The transition states are changing by linear scaling relationships. And I can think of this in terms of what I want based on how many steps there are. So in a simple toy reaction like this, A goes to B, I want one state where it's easier for A to get to B. So the barrier here is lower than in state 2. But at this point here, I've done something really well here, but I can't desorb. So I flip to state 2, and now B star could desorb to B in the gas phase. So I've made the catalyst optimal, or at least better, for each point in the reaction at that moment in time. So we can take these toy systems like this, simulate them, and try to understand what kind of design principles exist out there. And so here's what a simulation frequently looks like. Here is a surface, and I'm changing it from very strong binding to weak binding, and back and forth with a simple square wave. I can track what's on the surface. So sometimes that surface is covered in the surface product B star, and sometimes it's covered in the surface reactant A star. And then I can track what's coming off the surface. So at some moments in time, when the catalyst is flipping very quickly, the turnover frequency, the instantaneous turnover frequency shoots up, I deplete the surface, and the rate of reaction comes back down. So you can see here immediately your first question is, well, why don't I just oscillate faster? Why don't I oscillate at larger amplitudes? All these types of questions. And this is what we've been thinking about. But I can put all of this together and say that there's definitely a condition that you're looking for that's optimal. So forget the right side for a minute. The left side, there's a lot going on here, but the left side you've seen before. This is a Sabatier volcano. That's the best you could ever do. And this and here's the other side of the volcano. This is the extension of those independent catalytic rate or binding energies. This is the tie line for a paired dynamic system. Now, what types of reaction rates do you get out of a system like this? You can read off the right. So this is the frequency I apply to my catalyst on the bottom right. And this is the time-averaged rate of reaction. So just think of this as a rate of reaction. So if I'm flipping a catalyst between states very slowly, think about it. From the perspective of molecules, they don't know the catalyst is flipping, because their entire lifetime of reaction is happening so fast, or relative to any change around them, they just think they're a static catalyst. So down here, the reaction behaves as if it's on the Sabatier volcano. Now, as I speed this up, eventually I hit this parity line where the molecule, the time scale of the reaction, the molecules start to sense that the catalyst is changing around them, and I start to accelerate. And I accelerate past the Sabatier peak up to this point right here. And at this point, I've hit the rate limitations of the independent elementary steps. At this point, I can't react any faster, and I can't desorb any faster. So my rate of reaction hits that maximum. Now, if I were to go any faster, I would be flipping the catalyst, and there would be no inherent benefit to doing so. I'd just be wasting energy. So there's this quantity we track called the effective rate. It's a combination of the reaction rate and the efficiency that tells you there's one frequency that you would want to operate at for any particular dynamic catalyst. And that's what we call the resonance frequency, because we're pairing the natural frequencies of our system, that point there and there, with the frequency we apply to our catalyst right there to give us a maximum performance. Okay, so what we're essentially doing is very simple. I have a catalyst. It's going to go through a sequence of things. This is a very simple one because it only has adsorption, which is very fast anyway, reaction and desorption. So the catalyst is in two states. Right here, B can desorb. When it's a positive charge like that, you can see A star forms B star. That's that pink transition state. And it's favorable for each of them. Now, this is where it gets much more complicated, because these toy systems, they're very simple, but real chemistries are quite complex. And on top of that, it's not obvious if I have two states, if I have two steps that matter, I clearly want a two-state program. If I have 3 states, 4 states, parallel reactions, this complexity goes up significantly. So over here in the middle, I have some mechanism for doing this. I've shown you this condenser. It could be light, it could be strain. I'm interested in accelerating reactions. I'm interested in controlling selectivity. I'll say something about that in a minute. And the weird one here is conversion. I'm interested in controlling the conversion of the reaction. So hold on to that thought for a minute. Into this program now, I can write anything I want. I can give it multiple frequencies. I can give it different shapes. I can do combinations of frequencies. It's not obvious immediately what to do right here. And so we've been focusing a lot on thinking about this and making devices. But let me come back to this point right here, because there's something very strange that happens when you apply these dynamic systems that I was not anticipating. Let me show you a simple simulation. Okay, there's a lot of data on that, maybe. Okay, I think my computer got tired. Okay, so let me show you a simple simulation. Let's take a toy reaction, A to B again, in a batch reactor, and I'm going to apply these dynamic perturbations. So over here, I can start out that batch reactor of any composition I want, 100% product or 100% reactant and everything in between. And I'm going to let that reaction go until it stops changing. And what you see right here is the reaction proceeds to a steady state, which is different than equilibrium. And then if I turn off the dynamics, the reaction comes right back to equilibrium. If I turn them on, they go back to their steady state. So this, of course, when we ran the simulation, we thought our code was wrong. Then we panicked for like 3 months, and then we started reading about ratchets in biology, and then we felt a lot better. But what's happening is actually very simple, conceptually. If I look at this reaction right here, this isn't the reaction over here, but it's the visually the easiest way to see this. This is, of course, an uphill reaction. And if I think of the blue state, the red molecule can't get over this huge barrier. So it waits for the green state, and then it can easily hop over that barrier. And then right here it sits until it comes up to here, where it can desorb. Now, the desorption barrier is much lower than the reverse barrier, and so there's no good mechanism for purple to go backwards in this particular system. So we're using this energy input here. We get some energy out here. We put a lot of energy in here to put the catalyst in a state where there's a preferential kinetics forward but not backwards. And that can drive a reaction, in this case, forward. This is actually only a 20 kilojoule per mole perturbation, and I get about 30% difference in the steady state conversion versus equilibrium. Now, which way does a ratchet go? Does it promote a reaction past equilibrium forward or to lower conversion? And it turns out it depends on the program you put into it. You can drive a reaction forwards or backwards by changing that signal you give it. So here's an example. Green here is equilibrium. This is part of the input program parameters I pick. This is the frequency I apply. At low frequency, it just goes to green, which is equilibrium. As I increase the speed at which that catalyst is flipping, I can either drive it forwards to almost complete conversion or backwards to almost complete unconversion. And it's only, we found this data like 4 years ago, it's only in the past summer that I came up with an equation for how we could define whether it goes forwards or backwards, which is a lambda parameter. Okay, let's put these ideas together into one big thought here, which is a real reaction, which is what we care about. The energy reactions are multi-step. So A star to B star to C star to D star to E star to F star. I now have all of this immense complexity of how I'm going to design a chemistry. So if we could break it into individual units and understand how each elementary step behaves, I could think about designing complex reactions with dynamics. So take a single step here and think about the catalyst only existing in two states. State 1, which is weak binding in blue, and state 2, which is strong binding in green. Now, as I flip this system, it's going to exhibit 4 total rates. It's going to forward and backwards in each state. And the nature of the ratchet is there's favorable kinetics one way versus the other. So 2 of these are very slow. So D star is not going to go backwards, C star is not going to go forwards. But the relative kinetics between C star going forwards here and D star going backwards there are what matter. So if you look at this, you can think of it this way. Purple can go backwards to orange, but orange goes very quickly back to purple. So this is definitely a forward kinetic system, and you can see that also right here. It's very quickly for molecules to go to a very low surface coverage, and they very slowly come back. So the nature of a ratchet is competing kinetics of the 2 fastest steps of the 4 possible rate coefficients. Okay, so with that idea in mind, we can take any particular catalytic ratchet and start to describe it. Essentially, what can happen is this kinetic bias of promoting a reaction forward or backwards against equilibrium only happens at high enough frequencies. And that frequency cutoff is actually can be determined based on the K values you're using, which are temperature dependent. So here's where the ratchet is on at high frequency, and it's going to be off over here. And actually, I can define that behavior by comparing simulations to some simple equations right here. And that gives me the kinetics that matter. So putting this together, if I think of this is an example catalytic ratchet that can do everything. I picked it because I can make it go forwards or backwards by changing the duty cycle. So if I think of any particular elementary step in a multi-step reaction, I need to know three things. Is that particular step promoted forwards or backwards? And I can calculate that with this lambda parameter. Number two, is it on or off? Is it exhibiting kinetic bias, or is it just too slow to matter? And so I can measure its cutoff frequency. So every elementary step has a cutoff frequency. And number three, I care about when we have a favorable direction. Is it in weak state or strong state? And so when I string these together, it's going to matter because the molecules have to move from step to step to step. So three pieces of information here I need for every step of a reaction. So let me make a simple toy example of a real chemistry to help you thinking about this. If I'm trying to convert A to E, I can have a whole series of elementary steps, and they can be in series, they can be in parallel. You can even have loops. I'm skipping here about 30 minutes talking about the kinetics of loops under dynamics, but under dynamics, you can actually drive molecules in loops in a way you can't in static systems. In this case, if I look at each one of these, I have a frequency, a cutoff frequency, I have a directionality, this one's forward, this one's backwards, and I have whether it's a strong or a weak pass system, and I can take this entire reaction system and plot it over here. So the frequency I apply, if it was 500 hertz, all of these would be on, and this one would be off in terms of its kinetic bias. So if I take this simple picture, once I've taken every step, calculated its three parameters, I could interpret it this way. This molecule can get to F on the strong binding state. In the weak binding state, F can get to G. And then in the strong binding state, G can go to E because this reaction right there is turned off at this frequency. If I went above 1,000 hertz, this would be a problematic step. Okay, so this is what we're now applying to real chemistries, which is what I'm going to end with. But let me summarize these ideas. This idea of dynamics in complex reaction mechanisms requires us to have some fundamental understanding. And so what we've been doing is putting these ideas together in our center for the last 5 years under the name catalytic resonance theory, because we're trying to match the frequencies we apply to the key natural frequencies of chemistry. The key one I started with was talking about speed, and that is I can accelerate reactions potentially beyond the Sabatier peak right here. Number two is I can drive reactions using energy input in the ratchet mechanism away from equilibrium. And the one I didn't talk about, because it would be another hour talk, is when I have this complexity, I can drive reactions down different reaction pathways. There's a whole paper we wrote where you can say if I have a reaction that's never selective to one species, can I use dynamics to drive it only to the species I could never make in the past? And the answer is with these toy reactions, I can definitely do it. We're trying to build out this theory to understand how we design systems to select for anything. Okay, so our center focuses on putting all of these ideas together. I've been talking a lot about this idea of catalytic resonance theory over on the left. I started out actually by talking about making devices right here. We're doing experiments that go with this, both vacuum experiments, spectroscopy, and we're building flow reactors to get to that point. And then programmable surface reactions where we do calculations and kinetic modeling of these behaviors. So let me end here with two examples of simulations of real chemistry. This is work done with Dauenhauer at the University of Delaware. We were studying the nitrogen and hydrogen reacting to form ammonia. Nitrogen splits apart on two sites, a terrace and a step site. So then I have nitrogen atoms on the surface. Then I add a hydrogen, I add a hydrogen, and I add a hydrogen to get NH3 on the surface, and then that comes off. This has all this complexity of series and parallel reactions because molecules can move between sites, terrace and step sites, and I'm adding hydrogens. So in this system, what we're going to do, this is on ruthenium, we're going to strain that ruthenium with time, and we're going to strain it at different frequencies and different amplitudes. So what you see here, I pulled off what I think is the most interesting part of this whole paper. I can take this reaction, turn on the simulation, and it goes to this equilibrium at these conditions. And then when I apply dynamics, at low frequency, the reaction goes backwards, and at higher frequencies, 1,000, 3,000, 5,000 hertz, it goes forwards. Now the benefit here, and this is shown in the rest of this paper, is that I could achieve comparable conversion at lower pressures than we conventionally do. So normally this reaction is run over 150 atmospheres. It usually requires massive capital, massive size. It's difficult to scale down to something we would want to use for the application of storing renewable power in electrical and in chemical form. So there's a lot more to this paper, but I wanted to show you this example right here. And of course, when we turn off the dynamics, the reaction comes right back to equilibrium. This next one is the one we just wrote, where we were thinking about this idea of we can apply this to thermochemical reactions. You could do the same thing to Faradaic chemistry. So in this case, this is the oxygen evolution reaction. This is work done by Dr. Sally Gathman, where we're taking water and evolving oxygen in these 4 steps, which is 1/2 of the electrolysis chemistry. This reaction has a very well-known overpotential volcano, which is just another way to plot the Sabatier volcano. You can see right here. Here's the overpotential. Here's the volcano descriptor down here. And you can see iridium oxide sits right up here at the top. And so we've taken a model of this system, and there's one of the parameters we build into the model right here, just so we could say over a huge range of possible model parameters, we see comparable behavior. So we take this conventional overpotential volcano and we turn it into what we like, which is a rate volcano. So over here, the dashed lines are another way to express the model right there. And then as we oscillate the binding energy of molecules on the surface using something like our condenser, we can accelerate this at different frequencies and different overpotentials. So you can see right here, this is our current target for oxygen evolution. This is what we would achieve with 350 millivolt or 250 millivolt overpotential. And with dynamics, we can accelerate these reactions about 60x. Another way to say this is we could achieve comparable performance with lower applied overpotential. And so that's the potential idea of this approach, is that we could either use less energy or we could accelerate the reaction to get more throughput per area, which would allow us to use our metals and materials more efficiently. So let me end right here and just say what I really like about this approach is, a lot of times people say to me, what's a good catalyst for that reaction? And there's no inherent way to know this without knowing a whole lot about materials. And we know a lot about materials now, which is good, but this approach is more of a strategy. I can take a perturbation method, light, strain, or charge, and I can start thinking about what I'm going to modulate with time and how fast I have to do it for what I want to achieve. Do I want to speed up a reaction? Do I want to be more selective? And so I think, like I said, we can use this strategy to go after all the things we care about potentially if we can make these devices and techniques powerful and fast enough for these types of applications. And they apply to the biggest targets we're going after: hydrogen production, CO2 conversion to methanol, ammonia synthesis, selective oxidations. And I say immense work remains because you can see we're only kind of in the first part of this. We've only been making condensers for a little over 2 years. And we're trying to make them more powerful, faster, and apply them to real chemistries. So let me end right here. We're a Department of Energy funded Energy Frontier Research Center. There's a whole bunch of catalysis people in our center, obviously working together on these types of problems. This is a picture from our spring meeting in Minneapolis. Omar Abdelrahman did some of the work you saw right here. Dan Frisbee made some of the devices. Matt Newrock did some of the calculations. So thank you for the invitation, and I think we have time for questions.
Thank you. Wow, that's really loud. Sorry, I blasted everybody. That was really interesting. I have a question about essentially flux matching in the sense that if you think about when people are talking about driving reactions, for example, electrolysis with PV or something, and you're coupling devices, and you have to really think about the flux matching in order to make that work. In some sense, so can you comment on, to me here, the flux matching has to do with the frequency, the oscillations, so the time scale for that frequency oscillation, and the actual rate of the elementary step. And if that's not right, I'd like to understand why. And whether or not you can actually match that, because usually those rates are much faster than the frequencies you're talking about.
Yeah, so that's a great question. I get something like some variation of this question a lot. The question is, what do I have to match? You're saying flux matching. Normally I think of like how much light has to come in versus how many molecules or need to react or something like that. In this case, the equivalent kinetics that matter are how fast I change the surface. So for this, that's why I was pointing out that impedance spectroscopy, where I said these devices can move charge back and forth 1,000 times a second. That's a frequency that matters for what we care about, because we're not interested in the time scale of a single elementary step turning over. We're interested in the ensemble. So if I rate a rate expression, the k value accounts for, the time scale of interest is the inverse of the rate constant, which is much slower. And that's why we're interested in frequencies that are around 1 to 1,000 hertz, that kind of range where we'd either match or exceed the frequencies of turnover frequencies of reaction.
So when you say you're talking about the inverse rate constant, you're talking about the k observed then. You mean the overall rate constant?
So it's more complicated than that because I care about more than one rate constant. So see if I can find this quickly. So think of it this way. If I have two steps that matter in the simplest case, there's two time constants that matter. In this case, this is the desorption rate constant and the reaction rate constant. And when I apply an amplitude at these conditions, I've time matched those two. So that we've shown if you take your amplitude of oscillation here, the purple, and you slide it left to right, you haven't matched the time scales anymore. If I slid to the left, this point here would move up there, that would get faster, but this would slow down. So horizontal tie lines here match the kinetics of those two steps, and that's the frequency I care about. So it's not the k overall, it's the k values of the independent steps. Now when we get to systems that have degree of rate control spread out through a system, it's going to get much more complicated.
Thanks. It's loud. Thanks very much for that. Really, I think it's either on or off. It's kind of binary.
Let's hold it back.
A bit like your reactions. So maybe this is an unfair question. It's maybe for Dan Frisbee, not yourself. But I couldn't really understand the device and the role, for example, of the graphene and whether it's a diode type deplete. It wasn't clear to me what's actually happening. And so I understand about your hafnium oxide, the high dielectric constant. But it's kind of a cross between a capacitor and a diode. And what's actually happening? And my this is really annoying. My second question is about the generality of this process. Is propanol unique in having these reaction pathway minima, or can this be applied really broadly to most catalytic reactions?
I'll start with the first one. I'll try to answer it best I can. So the goal of the hafnia, of course, is to, just so people understand, we don't want current to leak through. So we want an insulator. So people have used things like silica or alumina, but those are good insulators. They don't allow leak current, but they have a low dielectric constant. So we're always kind of balancing these things. What we want to do is to accumulate these matched charges on either side. The graphene is what allows us to move charge horizontally. Now, if we used a completely thick layer of metal there, the top surface, which is exposed, would never feel the electronic effect, because charge is going to accumulate as close to that hafnia as possible. And so the benefit of graphene is it gives us high conductivity, but low density of states, such that we can essentially overwhelm it, and the platinum atoms interacting with the graphene feel that electronic effect. Now, related to this is how far into the cluster does this go? Obviously, if you make this stick, I actually showed this data, the platinum on the top feels no effect of this. It's too far away. So obviously, the smaller the clusters, the better. That's one of the things we're working on. But other geometric arrangements here actually get more of the active site closer to the oxide.
So a thin layer of gold is too thick?
Thin layer of gold is too thick, actually. Yeah. Your second question, I can't remember what it was.
Just generality of this. I mean, does every reaction have these
Yeah.
minima?
So if I come back to you, see if I can find this quick. If I come back to this picture. So the question is, what material should you start with? You could start it with something at the top and then try to push it to the left and push it to the right. Or maybe you could pick something on the left and try to push it all the way over to the right. We don't know yet. So a key question here, and this is something Matt Nurok and Rachel Getman and Lars Grabo are working on, is do we see the exact same scaling relationships with charge as you would see with periodic variation? In other words, when I'm changing this binding energy with charge, does it give essentially the same properties as with different metals? So far, with some materials, the answer is yes. With other materials, the answer is no. So it's the broad applicability, I don't know for sure that we could solve every problem. I mean, that sounds ridiculous to say, but like the broad applicability, we don't know for sure yet. There's too much uncertainty.
hold it away. So the other question I had is, it looks like to see a reasonably large effect, like 20 kilojoules per mole, sometimes you have to go to as much as 6 volts. That sounds really not very practical.
So that's a great
Do
question.
you have something to say about that?
Yeah. So a lot of times, if you're thinking of this as a Faradaic reaction, a 6-volt over potential sounds enormous, right? But this is non-Faradaic chemistry, so we're not applying there's no net current under these voltages. So you can't think of it the same way. That's a simple answer. Number 2, though, is as we make these devices more powerful, the total capacitance goes up, we can work at lower voltages.
So wow, okay. I'm curious, from a fundamental point of view, if you knew the mechanism of a reaction, of a 5-step reaction, let's say, and you knew the inherent, the elementary step rate constants, and each had its own unique frequency, is that you could then make a program, I would imagine. It's a multiple frequency, looks sort of like an interference pattern that's coming and going off of the device, right?
Right, that's what we're doing with simulations right now. So the closest we've come to doing this reaction is what Phil Christopher has done. I didn't talk about it, but he was studying a reaction where he pulses light. So he takes a reaction, methanol decomposition, which is CO poisoned. So you form CO, and then it desorbs slowly, and then he pulses with light. So that's the equivalent of this type of system. With these complex chemistries, we're still trying to make a condenser powerful and fast enough for their application. But on the simulation side, we're doing right now what you just said, which is we can calculate for either charge or strain or light, well, not necessarily with light, what the effect is of the perturbation, and then we can try to optimize a program for it. So there's more people working on this than just people in our center, because we actually need a lot of people that do optimization strategies. So it almost becomes a systems problem of how you design the best input program for a complex mechanism. Gotcha. We already know that there's a simple principle, which is as the reaction gets more complex, the input program gives better performance as it gets more complex, which is good and bad. But
on the flip side of that, and maybe this is totally naive, but could you go the opposite direction potentially and probe what the mechanism is by looking at different programming?
I don't know the answer to that. That's like impedance spectroscopy for reactions. The one thing we're doing that's reverse is, let me tell you real quick what this is. So you can use these devices in reverse. And this is a series of papers we're writing right now. If you take a molecule and you adsorb it to that surface, there's charge transfer. And you can actually measure that. It's fractions of an electron per molecule adsorbed. Now, the more electron transfer you have, the easier it is to modulate that molecule. So molecules like hydrogen, we have very little electron transfer on a surface. And so it's actually very difficult to modulate hydrogen binding energy. But molecules like CO or ammonia, very strong electron transfer. It's like 10% of an electron or something like that. A huge amount.
Yeah, I'll take one. So when you're talking about dynamics in this case, it's centered around the molecule's interaction with the surface. But what about dynamics of the surfaces themselves? Do you see, particularly in the case of the smaller nanoparticles that are sitting on the surface, are they restructuring under these conditions? Are they sintering or doing other artifacts?
I don't know the answer to this yet. So, like for example, what you were just saying a minute ago is exactly a great question. If we apply a large bias to this, do these clusters, which of course are cartoons here, do they give the same facets? Do they prefer to be in different shapes? I mean, if you give it enough charge and you accumulate that much positive or negative charge, they're gonna do something. I don't know what. So right now, what we have is it's taken time, but we have the ability to put a holder in our STM where we can apply a bias, stop the bias, image it, and then come back and look at it again under different biases. And that's ongoing. But I don't know, this is where Matt Nurok is calculating kind of what we expect to see between clusters and different shapes and applied charges. The one thing we know that's probably intuitive is that charge does not distribute evenly throughout that. It prefers corners and edges, which is actually really good because that's where the active sites most frequently are.
I actually have a question about the configuration. Do you hold the voltage V cap on the whole time. So I'm wondering if you could replace hafnium oxide with a stronger ferroelectric, so you could hold charge separation even without turning on the voltage.
So we have actually looked at ferroelectrics. If you polarize them, they will stay in their polarized state.
Right.
And actually, ferroelectrics are excellent materials for this. And that's all I'll say for now, because it's something we're working on.
Because hafnium oxide is partially ferroelectric as well at certain thicknesses.
But there's way more powerful ferroelectrics. Yeah.
Right, that would work better, right?
It's a great question, yeah. I just don't want the ferroelectric polarity to be so large that it's hard to flip it between different states. So.
You mentioned there's a directionality to elementary steps in this dynamic system. Is that something that's inherent to the chemistry of the reaction and not something that, so are you able to flip the direction, the directionality of it based on your dynamic conditions?
It's a property of the chemistry and the scaling behaviors, but we can modulate that to different sides of directionality. So I showed that one plot was green, red, and blue. So depending on how I bias that, I can push it from forward to backwards. Yeah. The question is, in a sequence of reactions, are there some that I need to flip? Right.
We thank Paul again for a great talk, and thank you all for coming.
Thank you.